Hello, everyone. My name is Thomas Kim. Today is March 8th, 2023. I'm very happy these days. Electricity and magnetism. From this book, we will solve chapter 2.7, example 2.9, 2-point charges of opposite sign. Electric dipole. This example, we will solve all the problems in chapter 2. We will also solve chapter 2.8, multiple expansion, through next few episodes. This example is by no means simple. We have to expand vector as a Taylor series like this. This formula looks very scary. Then we will assemble the parts to compute electric potential. Last night in my dream, I solved all these things. If you keep watching my videos, you can also solve these problems too. Though this problem looks very scary, we will completely master electricity and magnetism. Without further ado, let's get started. Open up Visual Studio Code. Select empty space. Click this button. 015 E from P. Click this button. EFP.txt. Hit enter. Ctrl V. I will close welcome window. We are given a scalar function MIT phi in BBR3. Of course, MIT is called electric potential. L2 Q. Phi is electric potential. Then the electric field BB E equals negative nabla MIT phi. When the electric potential is given, we can easily compute electric field E by taking negative gradient over P. Now we go the other way around. We are given BB E, the electric field. How can we compute electric potential phi from electric field E? I will copy and paste. Then we go the other way around, like this. So we are going the other way around. Now we perform dot product. D BBR C dot BBR Alt Q. I missed D here. We perform dot product on both sides. Then from this we take int, also int. Now how can we integrate these things? For any scalar function MIT f, the MIT f equals nabla MIT f dot d BBR. So from this, in place of phi, if we substitute f, this left hand side becomes int d MIT phi. This is MIT phi. Now, from this equation, the left-hand side, this side is P, but this result is not very accurate. We will discuss this in your future sessions. I will fix my wording here. For any scalar partially differentiable function, df equals gradient f dot dr holds true. So thus, I will copy this, paste MIT P. This is MIT P. In my next episode, I will explain this identity in gory detail. Also, remember this. df equals gradient f dot dr can be also denoted dr dot del f. df equals gradient f dot dr. This formula is important. Also, df equals dr dot del f. This formula is also important. Please keep these identities in your memory. Now, let's move on. What the heck is this nabla operator means? Or what the heck does this nabla operator mean? When we play football or soccer, we use the balls. When we play football or soccer, we play against the balls. When we play games with the nabla operator, we play against the position vector BBR or the displacement vector BBR minus BBR prime. Nobody ever taught me this trivial or simple but very important fact. Nothing can beat comparison when it comes to any learning. I will give you concrete comparisons. Suppose we are given a scalar function MIT f is ln natural log MIT x. We learned its derivative is em dash d MIT f over d MIT x equals em dash 1 over x. If you have learned calculus, this must be familiar with you. Now we are given MIT G. This is ln R, where BB equals x BB plus y BB plus g BB and R equals magnitude of R. So we are given magnitude of position vector. So we can play with the nabla operator. Then nabla MITG equals em dash 1 over R. Here MBF R, where MBF R equals em dash R or the unit vector over BBR. If this is not very convincing, I will give you more examples. Copy. I will make demarcation. Paste. Now our function is simply x. We learned its derivative is 1, like this. Now we are given r. It should be 1, but unit vector. I will remove this part. This r equals r over its magnitude or unit vector. Because I'm rich and generous, I will give you unsparingly. Now xn, its derivative will be nx minus 1. Now g is r to the nth power. Then n r n minus 1 r. Please note, when g is function of r, its gradient can be also written like this. We will substitute r with this vector em dash r over its magnitude is r, because this part is a unit vector. From this, we can say n r minus 2 r. I will fix this part like this. This is equivalent to this, but try to memorize this way. Vector calculus is simple. With this book, Vector Analysis, you can completely master vector calculus. But running vector calculus with this book alone is not very fun or interesting. However, you learn electromagnetism side by side with vector calculus. You can master vector calculus as well as electromagnetism.